Welcome to the second episode in a series where I make a solar panel control system for my house. In this episode, I will walk you through the design and demonstrate the functionality of the power supply I made for this controller. Now if you're thinking, power supply boring, well fair enough, that probably would be my reaction too. But I think this power supply implementation is pretty interesting, so that's why I get its own episode here. Anyway, let's get straight to it. For this power supply, I simply need to make a 5-volt rail to power the system. A 3.3 volt rail is also needed for various devices, including the ESP32 itself, but the ESP32 module I'm using includes a 3.3 volt regulator, so that takes care of that. The source of power that I will use will be the solar LiFePO4 batteries, normally around about 24.6 volts, but really they range from anything between 22.2 volts and 29.2 volts. To get the 5 volt rail from that, I will use a LM2596S voltage step-down module adjusted to output 5 volts. This can handle input voltages up to 40 volts and can supply a maximum current of around about 3 amps. It also has a conversion efficiency of up to 93%, but practically I expect it to be around about between 60 and 80%. But this is still much better than using a linear voltage regulator where, considering the huge voltage drop, the efficiency would probably be closer to 20%, with the rest of the power being burned off as heat. So there you go, we got our 5 volt rail all done. End of this episode. See you next time. Well, not really. To add to the complication, I also decided to add an internal battery backup to the controller. Yep, you heard it correctly, I added a battery backup to the controller of a battery backup system. But maybe this is not as insane as it sounds, as I've already experienced a case where the solar batteries actually have gone completely offline. So having a battery backup system inside the controller itself actually will help maintain diagnostic capabilities even in the worst case scenario. For the battery charging, I'm again using an off-the-shelf module, this time a TP4056 lithium battery charger board. Actually, this module is pretty nice, as it can charge at rates of up to 1 amp, and it also has a built-in overcharge and over-discharge protection. Using the module is simple enough, just connect the battery to the battery terminals. In my case, I'm actually going to use 2 batteries in parallel, so to increase the overall capacity. Then supply 5 volts to the input on the module. Actually, this board has a USB connector, which is pretty nice, but you don't actually need to use that. Instead, you can actually solder directly to the terminals provided on the module. And finally, to access the battery output, you need to connect the output terminals on the module itself. So you can't actually connect directly to the battery, because by doing that you would actually be bypassing the protection mechanism that's built into the board. And as you would expect, the battery voltage output will be between 2.7 and 4.2 volts, depending on the state of charge. So that low voltage is going to make using a linear regulator impossible to extract a 5 volt rail in this case. So instead I use a MT3608 power boost module and adjusted that to get the 5 volt output. And really that's all the basic parts you need for a simple battery backup system supply. But to improve the design a little bit more, I also added a bypass circuit. And that allows us to, instead of always having to run the power through the TP4056 battery charger module, in normal operation it will actually be bypassed completely. And in that case, only when the external power disappears will the power then switch to using the output of the TP4056 module. And alternatively, when the power is present, the TP4056 module will either be charging the battery or just sitting idle and not playing any part in powering the system. Now I have to admit that this bypass circuit idea is actually not my idea. It actually comes from a video by Andreas Spiess. However, in that case, he actually uses this TP4056 module as a solar charger system. It's definitely an interesting video and worth a watch, so check it out. I'll put a link in the description for that. In any case, the basic design uses a P-channel MOSFET, a resistor, and a Schottky diode. The Schottky diode is actually what creates the bypass path that the external power supply will normally run through, and the P-channel MOSFET will switch in the battery power when the external power is lost. Electronics-wise, it's actually pretty tricky how this is working, and just by looking at the circuit, it's not immediately obvious how it actually works. But I'm going to avoid any lengthy explanation here, but I will point out that a similar concept is used in reverse polarity protection circuits, which also uses a P-channel MOSFET in a similar mysterious way. Google it if you want to find out more. Probably the biggest reason for me adding this bypass circuit in this design is to improve the power efficiency a little bit more, but I also hope it will reduce the wear and tear on both the batteries and the TP4056 module, and that should also improve the long-term reliability of the system. Alright, with the basic power supply now complete, let's get into a little control and monitoring. So working on this design, I did have a couple of ideas floating around in my brain. It's pretty hard to sort of identify how and when things actually crystallize, but the next part of this design effectively solves 2 concerns that I had been thinking about. The first being about battery reliability. Experience tells me backup batteries always fail when you need them the most. So how can we test the battery's health and be sure it'll be ready to perform when we need it to? Now the second concern I had was possibly overthinking things a little bit, but I wanted a way to remove the controller's power load from the solar batteries should the solar batteries drop critically low. And the idea here is to try to minimize the chance of the batteries over discharging and disconnecting from the power bus like I'd experienced in the past. So to test the battery or remove the controller's load, both require finding a way to disconnect the solar battery power input from the power supply. Now the easiest and possibly the most obvious way to do this appeared to be using a relay in a normally closed configuration. And using a relay also keeps the ESP32 control nicely isolated from the 24 volt rail. And as the relay is not energized in normal operation, it's also not drawing any power. Unfortunately, the flip side of this is that it's going to draw quite a bit of current to drive the relay's coil when disabling the external power, and that in turn is going to reduce the battery's effective runtime. So I built and tested this solution and I ran it for a while, but unfortunately I found a bit of a critical flaw in the design. And that would be that the relay would sometimes get stuck and not switch when it was commanded to. If I tapped it pretty strongly, it would probably clear itself, whatever, but basically it wasn't working the way I needed it to. In fact, when I first connected the lab power supply to this system, I did actually notice a big spark on the end of the alligator clip, and this happened quite a number of times. So it was really at this point that I really suspected that this was going to be a bit of a problem. The spark is actually due to a huge inrush current that is caused by the LM2596S down converter, and this spark is just enough to slightly weld the relay contacts together when it switches to enable the external power supply again. Anyway, I've experienced this before in other projects using relays, and a simple fix is typically just to use a much bigger relay. But that's not really an option here, because a bigger relay is going to have a bigger coil that demands more power, and that's going to massively reduce the amount of battery runtime. Instead, I got my brain into gear and I designed a proper solid state solution. In this case, I use an optocoupler as the isolation mechanism to keep the ESP32 safe. To minimize power draw, the optocoupler is only powered when the external power is disabled. And I also added a red LED in series with the optocontroller's input circuit, and that makes it obvious when the external power is being disabled. For the main power switching device, I'm using a P-channel MOSFET in a high side configuration. So when the optocoupler is not active, I have the MOSFET being biased low, and therefore activated and passing the power on through to the down converter. I also added a blue LED to the output. This makes it clear when the external power is both present and being passed through. To disable the power, the optocoupler is activated, and that in turn will pull the control input of the MOSFET high, causing it to switch off. This circuit turned out to work very well, and I'm pretty happy with it actually. It wastes far less power, and of course I don't need to worry about any stuck contacts. And a quick side note here while we are actually looking at this input circuit, for safety I also added a 2 amp self-resetting fuse just next to the internal power input connector on the board itself. Alright, believe it or not, we're still actually done yet. I've got one more feature to go. Even though we can connect the external battery and force the internal battery use, we are still totally blind about the state of the internal battery itself. So to be able to see the internal battery's current and voltage, I installed a INA219. It's an I2C based bidirectional current sense module. And for your information, I run this module on 5 volts, but to connect to the ESP32's I2C bus, I needed to remove the built-in SDA and SCL pull-up resistors that are on the board. And so the actual pull-up for the I2C bus is being generated by another module that I have on the board, which is running on 3.3 volts. Anyway, with the INA219 installed, we can now monitor the battery's voltage, and we can also see the amount of charge or discharge that's happening on the battery itself. From this, we can deduce the internal battery's state of charge and track its accumulative charge or discharge, and this information can also play a role in the controller's decision processes. So that's finally really everything in the design. You know how it all works, so let's take a look at the real deal. We have all the various indicators on the board here. The red LED here indicates that the power is being blocked from coming into the power supply, so the external power will not come in. And the blue indicator indicates that the voltage is coming into the board. The step-down converter has its own sort of active LED over here. The battery charge unit has a blue indicator when it's idle and a red indicator when it is charging. What I will do is I'll just quickly actually disconnect the power from the board just so that we can see how it reacts when the power is totally disconnected. You can see there it's gone into the failed state. And this is just what I decided to do. If the power is totally disconnected, it can't control it anymore. The system will automatically still use the battery in any case because it just means it can't stop the power that's not there from coming in anymore, so it's a bit pointless. So I decided to manage this by blocking the automatic control if this such a situation occurs, and you'll have to manually recover that. So let me clear that
And you'll also notice here on the indicators on the user interface, we have this external power is present, external power input is enabled, which it is because it's not red, and the CPU powered by external. So the external power is present is effectively just detecting if I'm disconnecting that external power like I did here. You can see now it's missing, even though the external power input is enabled, and it's sensing a current discharge, which is why we see that the CPU is powered by the battery. I'll restore that. And now again with the reconnected I can see it's present, and the CPU again is now being powered by the external source. I'll clear that area. Alright, so enough of this meaningless sort of stuff. Let's have a look at how it actually works. So as I drop the voltage, so once I got to a low enough voltage, it's actually gone into the operating mode. And then as I pick the voltage back up and the battery on the main battery recovers, it allows us the enabled ability to stop it manually if we wanted to, because obviously the battery voltage is adequate. But as the voltage picks up to an adequate charge on the main bus, it automatically exits that operating mode, and the battery charger here automatically starts charging up to recover any lost charge, and I'm detecting that here. So this is fundamentally how it's meant to work, is that if the voltage gets too low, it will use the internal battery for as long as it has charge to do so, or until the main bus voltage recovers. So what I think I've demonstrated there are the two realistic cases. One is the critical failure case where the voltage just disappears and we just want the thing to keep supplying voltage to the controller while we have a chance to view and understand what the error was. And the other case is the normal operation, whereas the voltage is getting pretty low and we want to disconnect this system from the main battery so it stops drawing charge. So obviously when it's in charging I can't actually do much, but it should finish charging in a second because I've only used it for a little bit, so let's just wait for that. So there we have the charge controller stop charged, and now we can see that the controller here has detected that there's no current, so it's now back in the waiting mode. If we drop this voltage low enough, we can actually manually run this, because obviously that is a good situation for it to run. So it has to be, a little bit below 25 volts, obviously is the way I've set it, and then I can manually run it. And then the same rules apply. The voltage has to recover enough to get back out of that operating mode. And then we're back out. And obviously it's charging again, but it will come out of charging very quickly because there's very little charge that I've used. So if we're above that 25 sort of volt level, then there's enough voltage on the main bus to feel confident that the test can operate, and then still have enough capacity left to run in that sort of real operation circumstance. Let me just press the test button so you can see that it sort of works. And over here you can see as we hit the test button, the external power supply is disabled. The LED is off here, indicating that there is no more power being passed into the system. The down converter is not being supplied with any voltage, and the charger is not being able to do everything. So basically all this side of the circuit is dead. The battery is just supplying volt through the current sensor and into the up converter, and that's it. So obviously if we stop the test, we enable the external power supply back in, external power supply is on, and the charger is charging away. So in normal operation, this system shouldn't really activate, right? I mean, I don't want it to activate. The main bus voltage shouldn't drop below that 22, I think it's 0.4 volts in any case. But if it does get down to that 22.4 volts, well then the current draw by this could be just enough to trip the battery controller on the main batteries to actually disable any voltage whatsoever. So if that happens, which hopefully is a rare situation, this system will be removed as a load from the main bus for as long as it takes for the main batteries to really recover. So right now I don't know how often this will actually ever be used. It may never be used unless that very really rare situation occurs. Maybe there's like a week of cloudy weather and absolutely no power, but I don't think there's going to be any case with absolutely no power. So with that in mind, that means that this battery that we have, this battery backup, will never be exercised, so we don't really know the health or what's going on. So the idea of the test is to be able to test the health of the battery. And obviously I could sit here and do the manual test every so often to see how the battery is performing. And the test is just 6 hours of discharge. and after that it will charge itself up, and you can compare the discharge time and the charge time. And I've done that here. You can see on this demonstration I show on the screen here, and the charge and discharge amounts are about the same, and the voltage drop is quite reasonable, so you can feel confident that the battery's okay by looking at that test. So instead of having to do that manual test every so often by itself, there's actually logic built into the code that every Wednesday at 9:30 in the morning, if there's enough voltage on the main bus, it will actually switch itself into the test mode and record that information. Obviously, the historical information will be dropped into here. So the information and the historical information, when we have a look at it, we can see how long it ran for the last operating period, which is that nominal operating period where it drops between that, where the main bus voltage drops below that 22.4 volts, I think I set it at, and until it recovers. The charging period is just for as long as it detects that the system is charging, and it will track all of those figures. And the testing period. So in that automatic testing period, what you'll typically see is the testing period will run for that 6 hours, followed by a charging period, which will charge usually for a pretty similar capacity for as long as it takes. It seems to take about half the time, around about 3 hours, I think. Alright, so that's it for the demonstration of the battery backup system.
Now, I consciously decided not to talk about the ESP32 coding or about how I made that pretty cool web interface. Instead, I wanted to focus on showing you how I put it all together and how it basically functions. Even so, I'm sure that there are those of you in the audience who probably would like me to cover this in more detail, so I'll likely try to do that in a future episode if I can. Anyway, that's pretty much it for this episode. For the next episode, I will delve into the murky world of high current measurement. So, I'll see you then.